We've proven that B implies C in the invertibility theorem. Let's now show that C implies D. In other words, if the homogeneous linear system AX equals 0 has only the trivial solution, then the rank of A is n. So C implies D. And we'll start by considering a generic homogeneous system. So consider the, let's say, generic homogeneous system with we'll say n equations and n variables, n equations and n variables. So if you remember back in chapter 3, we represent a generic system will be simply to write out the terms this way. So xn equals 0, and we'll write the last equation, an1 x1 plus dot 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 ann xn equals 0. And so this is a generic homogeneous system, and if the system has only a trivial solution, if this system has only the trivial solution, well, of course, the trivial solution is the solution where x1 equals 0, x2 equals 0, all the way to xn equals 0. So in that case, the augmented matrix, or its augmented matrix, which will look something like this: a11, I'll write the first two terms, a12, a1n, and 0, a21, a22, a2n, 0, and the last row, an1, an2, ann, 0. So this augmented matrix, if the system has indeed only the trivial solution, then this matrix can be reduced using row reduction to the following matrix: 1 0 0 0 0 1 0 0, and the last row 0 0 to 3 1 0. Right? The only possibility, if the augmented matrix, if the linear system rather, has only the trivial solution, it means that x1 must be 0, x2 must be 0, xn must be 0, and so the reduced echelon form of the augmented matrix can only look like this. But then, well, count the number of leading ones. There are n columns and there are n leading ones, and therefore we can state then the rank of A is equal to n, and that proves the implication. So that leaves us with D implies E, and then E implies A. So D implies E. So if the rank is equal to n, then we want to show that the reduced echelon form has to be the identity matrix. So we'll say if the rank of A equals n, and we'll say, let's give it a name, and R is the RREF, is the reduced echelon form of matrix A. So it's the RREF of the coefficient matrix. Then, if the rank is n, then R is an n by n matrix with n leading ones, right? Because, well, the rank is n means literally that the reduced echelon form has to have n leading ones with n leading ones, and zeros everywhere else, right? So I can actually, here, let's remove the leading ones, and zeros in every other position. So zeros in every other position, right? Because if the matrix is in RREF, then above and below those leading ones we have only zeros, and therefore zeros in the entire matrix other than the leading ones. And therefore there's no other conclusion than, I'll write it here, therefore R is equal to I. That's the only conclusion we can come to, and therefore A is equivalent to I, because R is the RREF of A. And so that's the implication, D implies E. And finally, to close the cycle, we have E implies A. Therefore, if A is row equivalent to I, we want to show that A is invertible. But this will simply be the following: if A is row equivalent to I, then there exists a sequence of elementary matrices. We know this exists a sequence of elementary matrices. So we've seen how this works, such that, actually here, let's list the sequence first. So sequence E1 all the way to, we'll say, EK, such that So we've seen propositions that tell us that this is true, that if A is equal to I, then we have these elementary matrices that when left multiplied in this order by A will give us I. Then, as you can see, this, so we'll conclude here, therefore, A inverse is equal to that product of matrices, EK. This time I'm not putting commas. This is an actual product. So EK times E1. This entire product is A inverse, right? Because it's a matrix that times A equals I. And therefore, last conclusion, A is invertible. And this concludes the proof of the invertibility theorem.